Hello everyone, today we will present our algorithm and research in quantum computing.
My name is Sarthak, and my teammates are Shuhul and Jeffrey of Team Schrodingers Beavers. Today, we are going to talk about the quantum counting algorithm.
The purpose of this algorithm is to find the number of solutions to a given function. For example, consider an arbitrary equation with multiple solutions. The quantum counting, or QC algorithm, helps us find the number of solutions to this equation, which should then help optimize the search for individual solutions.
First, we need to define the problem explicitly. The oracle is a function that tells us if an input is correct or not. This is a specific function we're trying to find the number of solutions to.
The classical approach to this problem would be to run the oracle for every input and record the inputs that the oracle says are correct.
The quantum approach is to run the oracle for every input at once using a quantum superposition, and then selectively count the number of correct solutions.
In order to do this, we can use quantum amplitude estimation, or QAE. It amplifies the correct states and then uses them to tell us the probability of an input being correct.
The combined solution is to use QAE to get the probability of a correct input and multiply it with the total number of possible inputs. This will give us an estimate for the correct number of solutions.
Now that we know the algorithm, why is it significant? QC is quadratically faster than the classical approach and is used as a subroutine for many other quantum algorithms.
Some uses for QC are for Grover's search algorithm, which needs the number of correct inputs to find the values of the solutions. We can also check if a solution exists or not. Finally, this can be used to determine the existence of a Hamiltonian cycle.
We implemented the algorithm in Q# and imported it over to Qiskit to analyze the algorithm.
Here are the results of our resource estimation and practicality assessment. In general, the number of required qubits is the total number of counting qubits plus the total number of measuring qubits. The oracle that we tested on had a total of 5 solutions. In general, the more counting qubits seen, the more accurate our estimation will be. This is reflected in the errorless AER backend, where with 1 counting qubit, it produced the wrong solution, but the accuracy increased with more counting qubits. However, for any practical problem, the number of qubits will always be quite large, which causes an exponential increase in runtime. Due to memory issues in current hardware, QC is impractical today. Further, on the 2 other simulators, due to the large amount of noise and error on real quantum computers, there was low accuracy. However, there was still a chance that the algorithm would reach the correct solution.
We created an implementation of QC that lets us find the number of correct solutions to a problem.
The biggest takeaway is that the quantum counting algorithm provides many useful applications as a building block algorithm thanks to its quadratic speedup.
We also worked on the quantum KNearest Neighbors algorithm. This algorithm is used to classify images into groups, such as classifying airplanes or beavers.
The KNearest Neighbors is a classical machine learning algorithm that converts images into features, which are smaller processed representations of the image. Here you can see the feature representation of the grayscale beaver at the left.
The training images are the ones that we already know the class of. The test images are the ones that we want to classify. For k equals 3, the image classifier would identify this test image as a beaver.
We can compare the test image to all of the training images at the same time by, again, using quantum superposition.
Using a research paper as a guide, we created some of the required subroutines and code for the QKNN.
Here are some of the subroutines required for this algorithm. We implemented 3 of the 5 listed subroutines. The final 2 subroutines lacked adequate description, and 1 required the use of quantum RAM, a theoretical piece of hardware which doesn't exist. We were able to extract features, step 1, put those features in the quantum state, step 2, and prepare those images for processing, step 3.
To understand the paper, we broke it down into multiple sections and made organized notes on what we did and didn't understand.
Some challenges that we faced were that there were very few circuit diagrams and some steps were omitted. One section even required using quantum RAM. Unit testing was also hard due to entanglement, because we could not selectively dump the value of certain registers halfway through the program.
The paper puts forth an implementation with a certain complexity, but in reality, there's too much error in the subroutines that we were implement for it to be practical.
In conclusion, we see that quantum systems provide a significant speedup in both quantum counting and quantum KNN compared to classical systems. It is exciting to see the endless possibilities that quantum computing can bring to us in the future. Thank you for listening to our presentation.